Welcome back to Physics with Miyoshi. We're here today not to learn how to throw a curveball, but we're how to apply Bernoulli's principle. Actually, learn about a little bit about Bernoulli's principle and what that has to do with fluids, and a little bit about how that helps us to understand about how it applies to making a ball curve or making an airplane wing lift. It's all with Bernoulli's equation. So what is exactly Bernoulli's equation? Well, let's talk about what it means first of all. Well, when I have a volume of fluid and I want to raise it, and we're going to talk about an ideal fluid, which is, of course, if you remember from last time, non-viscous, and it also is has a steady flow. It's not incompressible. So when I take this volume here and it's at a certain height and I want to move it up to this area, even whether the volume, the hose has changed or not, the pipe has changed or not, then I have to do some work to get there. And that would be non-conservative type work. In other words, I have to put something in there to get this guy to move in there. So how do I do that? Well, if I go back to the work energy theorem, I can see that my non-conservative work has to be the energy at 1 minus the energy at 2, which is equal to my pressure at 2 minus the pressure at 1 times the volume. I know that that's got to equal my total energy at 1 minus my total energy at 2. And this energy is, of course, the kinetic energy, 1/2 mv squared. This, of course, is my potential energy, gravitational potential energy, and this is, again, the kinetic energy, which is 1/2 mv squared, and the gravitational potential energy back here at this end. If I do some manipulation and I get rid of the V, the volume, I can see that now I have the pressure 1 plus 1/2 rho V1 squared. Notice that that would be rho times the volume if I kept the volume in there, but I got rid of that. Rho V squared plus rho G Y1, which is the density times gravity times the height at 1, equals my pressure at 2 plus rho V squared at 2 and times the rho G Y2. And that just tells me that the pressure change has got to be equal to the density times the velocity squared plus the density times the acceleration due to gravity times the height. And the difference of those two would be the difference of my pressures. So we can rearrange these equations. Yeah, there's a little bit of math magic in there, but essentially all I'm doing is dividing by the volume to get to this equation and rearranging terms a little bit, and we end up getting Bernoulli's equation. So Bernoulli's equation, again, it has lots to do with making a ball curve or making a wing lift an airplane, and it's got a lot to do with fluids. And so there it is, Bernoulli's equation. Again, it's P1 plus 1/2 rho V1 squared plus rho G times Y1 has to equal the pressure at 2 plus the 1/2 rho V squared at 2 times rho times acceleration due to gravity times the height. So, thanks for tuning in, and we'll talk more about fluids, but thanks for tuning in, and we'll see you again on More Physics with Miyoshi.